A magnitude 7.8 earthquake struck San Francisco early on the morning of April 18, 1906. The event marked the first time that the consequences of a major U.S. natural disaster were recorded on film.
A subsequent report demonstrated that the earthquake occurred on the northern half of a single continuous structure that we now know as the San Andreas Fault.
The 1906 earthquake and subsequent fire killed more than 3,000 San Francisco residents and left over half the city's population homeless.
Today, nearly 40 million people live in California, with many of them concentrated in major cities located close to the San Andreas and other fault systems. What can we do to mitigate the potential damages and loss of life from a future dangerous earthquake?
To answer that question, we need to understand the nature of earthquake hazards. When earthquakes occur, the earth shakes for seconds or maybe even minutes.
However, much of the damage with earthquakes is not a result of the shaking itself, but may be driven by other factors such as the design of buildings and the underlying geology.
Our objective for this lesson is to familiarize you with the principal hazards associated with earthquake activity and the factors that can magnify their impact.
One obvious consequence of shaking associated with an earthquake is the collapse of buildings and other structures. Rapid vertical and horizontal movements can shift homes off their foundations, collapse multi-story office blocks, and destroy elevated roadways.
The colors on this map indicate the severity of shaking associated with the 1906 San Francisco earthquake. The red color indicates that shaking was most intense along the fault, and the transition from red to yellow to green indicates that shaking decreased as we get farther to the east.
This graph illustrates that instruments at some stations near the source of the 1994 Northridge earthquake recorded ground shaking that approached 1 G.
A vertical acceleration of 1 G is sufficient to overcome gravity, throwing objects into the air. Cities and areas of seismic risk typically have strict building regulations that require that new structures withstand accelerations of 0.5 G or more with little damage. Even 60 miles or 95 kilometers from the epicenter, there is sufficient shaking to cause damage to older buildings.
But shaking isn't just about the distance from the fault. Look again at this map of the 1906 earthquake. Notice this red area here around Santa Rosa.
Even though Santa Rosa was more than 30 kilometers from the fault, it suffered some of the worst damage as a result of the earthquake.
The underlying geology and building design can combine to exaggerate or dampen the effects of earthquake shaking. For example, the 49-story Transamerica Pyramid shook for more than a minute during a major earthquake, but no one was seriously injured and the tower was undamaged.
Buildings or structures have a natural resonance or frequency of vibration related to the motion of an earthquake. The greatest damage occurs when ground motion matches the resonance of a building.
For example, taller structures will exhibit greater oscillations back and forth with slower ground motions. In contrast, short structures like two-story homes will vibrate more violently with faster ground motions.
The same earthquake will produce different shaking effects in different earth materials. Bedrock typically produces more frequent, smaller vibrations, the type of shaking that is more likely to damage shorter structures such as two-story homes.
Weaker materials such as muddy soils can amplify ground shaking and produce larger, low resonance vibrations that are more dangerous for multi-story structures.
Elsewhere, the shaking may cause ground failure. Landslides can occur in areas with steep slopes, blocking roads and burying homes under debris.
Liquefaction occurs when shaking causes the compaction of sediment, increasing water pressure and causing water and water-saturated materials to be ejected at the surface.
In this example, a block of granite sinks into the underlying saturated sands when the material is shaken vigorously. Local structures, like the sand boils or sand volcanoes, are often produced as a result of liquefaction.
Elsewhere, liquefaction results in subsidence of the land surface and causes objects to collapse into the slurry of water and sediment. In the most extreme events, this can cause whole apartment buildings to collapse as the ground beneath them gives way.
Fault movement during earthquakes can result in adjacent pieces of the land surface being displaced by up to several meters. Some blocks may move up or down, others shift from side to side. This is one of the easier hazards to avoid. The general rule is, don't build anything on or near an active fault.
We see examples of the effects of ground shaking and ground failure following the magnitude 9.2 Great Alaska Earthquake of 1964. This remains the largest U.S. earthquake ever recorded. Liquefaction, subsidence, and landslides swallowed buildings and left behind a chaotic urban landscape. The town of Valdez was moved to a more stable location following the earthquake.
A tragic scene. Entire cities flooded, entire towns inundated, an unending stream of floating debris. Buildings, cars, people swept away in an unstoppable wave. It's a brutal reminder, tsunamis are dangerous and unpredictable. But what causes these giant waves and what can be done to minimize their impact? Tsunamis can strike with little warning because they're usually triggered by a sudden displacement of ocean water, like volcanic eruptions, landslides, meteorites, or, the most common culprit, earthquakes. In the deep ocean, a typical tsunami wave is barely noticeable and poses little threat. But the waves can spread out thousands of miles, rolling across the ocean at speeds up to 600 miles per hour. As the rolling water reaches the shoreline, the wave's friction against the shallower floor slows it down and raises its height. By the time it reaches the shore, the wave can be as tall as 100 feet. Unlike ordinary waves, a tsunami wave doesn't crest and break. Instead, it moves forward like a solid wall of water that crashes over the coastline, obliterating almost everything in its path. And just when you think the danger is over, it recedes, dragging everything back to the ocean. Tsunamis have multiple waves which can continue to hit the shore for several hours, causing even more destruction. The word tsunami originates from Japan, a country that sits on a geographic location that makes it an easy target for these natural disasters. In 2011, it was struck by a tsunami that claimed nearly 16,000 lives. But the deadliest tsunami in history is believed to be the Indian Ocean tsunami of 2004. The U.S. Geological Survey estimated that tsunami released the energy equivalent of 23,000 Hiroshima-type atomic bombs. An earthquake created an estimated 600-mile rupture on the ocean floor. This caused the tsunami to form and then travel at the speed of a jetliner, reaching over 11 countries, traveling over 3,000 miles, killing more than 220,000 people. Because they can strike so quickly with such deadly force, tsunami warning centers around the globe are on constant alert, monitoring underwater earthquakes large enough to trigger massive waves. Their ultimate goal is to alert vulnerable coastlines and give residents time to seek higher ground before a tsunami hits.